T and T prime. So since T prime is terminal, we get a unique, we have a unique map from T to T prime. We call this shriek. Let me call it shriek prime, I guess, because it's the map that is induced by our hypothesis that T prime is terminal. And similarly, since T is terminal, we get the same thing, but opposite. So similarly, we get a unique map from T prime to T. So this is induced by our hypothesis that T is terminal. Okay. So now we can think about what happens when we compose them, right? Because I kind of showed it they're isomorphic, so we're going to do maps back and forth. That's the first part. And the second part is to check these two equations. Okay, so now I need to check what happens when I compose them. So say now, if I compose them, so I'm doing shriek prime. So if I compose them to get this guy, then I have a map from T to T. And we talked about recently, someone asked me, there's only one possible map from T to T, right? Because there can be only one map from anything specific to T. There's only one map like this, and we know one map is the identity. Okay? So indeed, this is the identity. I have a map from T to T. There's only one map. And we already know one is the identity. So it has to be the identity. And similarly, just by exactly the same argument with switching the things that don't have primes and things that do have primes, we find that the other loop is the identity on T prime. So I've shown that they're isomorphic. And now I want to say that it's the only isomorphism. But actually, like, the component maps are the only maps. Right? There's only one map that we're allowed to have from T to T prime. And there's only one map that we're allowed to have from T prime to T. So of course it's the only isomorphism, because there's nothing else that could make up this isomorphism. Okay. Does this proof make sense? So now I'm starting to introduce you to the way that we argue in categories. Yeah.
Sorry, what is the bang with the prime actually equal?
So somewhere I gave a definition of terminal. So that I said that when we have a terminal object, we use the bang to denote the unique map to the terminal object. But now I have two terminal objects. So I said that the bang prime is a unique map that's induced by our hypothesis that T prime is terminal.
The uniqueness, or sorry, jump from bang compose with bang prime is the identity on T. What is getting us that that's required to be the identity?
So it's part of this definition. So I'm trying to show that our T and T prime are isomorphic, so they satisfy this definition.
Right. Sorry, in my head that sounds like we're using the assumption.
So I want to show that two things are isomorphic.
Yeah.
That's a statement.
Yeah.
So we need to check that they satisfy this definition.
Yeah.
Because it's a definition of isomorphic. So then there are four things that I need to supply. There's the F, there's the G, there's this equality, and this equality. Does that make sense?
Yeah.
So I've produced those four things. So I have this, well, this is F, the shriek, this is the G. This equality is the first equality, and this equality is the second equality.
I think, how do we know that the equalities hold?
Yeah, okay. So we know that the shriek prime and the shriek holds, that's good. Then we can compose them. We know that we can always compose two things that share a guy like this in the middle in a category. So then we will just get a map from T to T. But then we remember, again, that T is terminal.
Okay.
Yeah, and then just to finish, so then since T is terminal, there can only be, or there has to be exactly one map from T to T. It has to be exactly one map from anything in particular to T, so we plug in T, we find it's exactly one map from T to T. We've just produced one, streak, circle, streak, prime. But we know another one, which is the identity, and there can be exactly one, so they have to be the same. Yes?
For clarification, versus that can be, when you use, the symbol used in the terminal object is key, not top, right?
Yeah, but I just put that
The
right.
unit object in set, is that also key?
If I were writing this in LaTeX, this would be a capital T, and this would be backslash top.
Thank you.
Yeah, but they're just random symbols. Okay. Right, so now we've shown that terminal objects are unique, of the unique isomorphism. So in category theory, when we have this kind of fact, and I said last time that the definition of terminal object is an instance of defining something via a universal property. And so when we define something via a universal property, we'll see some more examples in the lecture series, but not the exact definition. I think when we define something via a universal property, we always get this kind of fact. So then we will talk about the terminal object. Or in a second, we're going to talk about the product. Because there could be many if for some reason you stop being a category theorist and you start investigating differences up to equality. But as a category theorist, there is only one, or there's at most one, up to isomorphism. Okay. So let's talk about another concept that's kind of necessitated by this. So here I use the word similarly a few times, and here I also said that, okay, I'm not going to prove the second part, so it's basically the same as the first part. So there's actually something technical going on there, which is called duality. So let me erase this. Okay, first I want to define a new category, given a new category. So, given a category C, we're going to define C op, so this superscript is op, and stands for opposite. So this is the opposite category, or this is the opposite of C. By setting the objects of COP, so we're going to find COP right now, so we want the objects to be, I think maybe I'll do it here. So, COP, we define this to have the same objects as C, and nothing has happened yet. And if we have com xy, this is going to be kind of small for you guys, but the subscript here is COP. So I'm trying to find the HOM sets in COP. I'm going to take this to be the HOM set in C between y and x. Okay. So this has the effect of giving us a new category that has exactly the same objects, and we just switch the direction of the arrows everywhere. So maybe I won't write it down, I'll just say it out loud. There's some more stuff to the definition of category that we should probably check. So let's just talk through it real quick. So we need identities in a category. So what's the identity here? So we have special morphisms that go x, x, and c. And so if we're wondering what's the identity in HOM C op x, x, well, it's defined to be HOM C x, x, so we just take it to be the identity there. And if we have composition, maybe I'll just draw this. We're thinking about whether or not we have composition in COP. So say that in COP, I have arrows that I want to compose. So let me draw what's going on in C. So having an arrow like this in C off means that I had an arrow like this in C. And similarly, having a tree like this in C off means that I started with a tree like this in C. So in C, I have a composition here. G circle F. And I let the, oops, that's the wrong order. Using myself opposite. Okay, so G circle, F circle G. And so then we let this composition, G circle F, we want to define this guy, so we define it to be this guy. Let you write it down more formally if you want, but this is the picture. Okay, and then we need to check a few more things. We need to check left and right neutrality of the identity. Like that we compose on the left or the right. With the identity, nothing happens. And we need to check associativity. And hopefully it seems reasonable that that just follows automatically from the same facts in CR. The left unitality will follow from the right unitality, and the right unitality will follow from the left unitality in C. And associativity is itself the vector. So that follows from associativity in C. Okay, we have this new category. And now we can use it to generalize things very easily. And we erase stuff. So first I want to give an exercise. A relatively straightforward one that you could do if you want to just check that you're understanding things. So you can check that if you have an isomorphism between two objects in C, then you still have an isomorphism between the same two objects in C dot. So here's one writing exercise, an example of the same way. So exercise, check the same rigorously with all the details that the op is a category. And check that if X is isomorphic to Y in C, then they're still isomorphic in C op. Yes.
I'm confused. Say we are in sets, and we are considering for the arrows, we're considering functions. So the opposite category, so we still have sets because we have the same objects, but then we have how can we reverse the arrows? Is it because we don't specify what arrows are?
Well, if you take the opposite of set, so set is a completely concrete, not arbitrary thing.
Mm-hmm.
Take the opposite of set, then we have still a completely concrete, not arbitrary thing. But yeah, if we have, so in set op, this is a category that's considered quite a lot. It's important for, or it's kind of underlying the thing that I called the unit one over there, so this is important. The objects, as we said, are sets. The op doesn't change objects. And we get, so we have a morphism from X to Y, let's call it X, for for a function from Y to X. So you can define a category in all sorts of weird ways. And I'm just defining this new category that has object sets and morphism from X to Y if there's a function from the set Y to the set X. I mean, it's a little wacky, but why not? So I just choose to draw the arrows backwards. Why not?
That's it.
Yeah.
Okay.
Yeah, like you could start with like a graph, a directed graph, and then you could just reverse all the arrows. Like if your original directed graph represented, I don't know, some like crane network or highway network or something, then your new one might not represent anything that came from the actual real world, but it's still a directed graph.
So basically, we do not provide a way to construct arrows to explicitly construct the object type, right? We just take backwards arrows, and we don't specify what those are.
No, it's extremely explicit. I say that,
I'm sorry, I'm confused.
so maybe to write it slightly more precisely, I say is that x, y is defined to be the set of functions from y to x. And maybe now it's a bit confusing because the notation in set and the notation in like an arbitrary category are the same. So let's say such that f is a function.
Okay.
So I give this extremely explicit definition. I take this very concrete set. Does that make sense? I mean, it's wacky, but it's completely concrete. Okay, any other questions?
Yeah, just to carry on like that, so this, I'm sorry, but this doesn't seem like we reverse the arrows.
Well, here I'm talking about the set of arrows from x to y.
Yes?
And I'm saying that they're the set of functions from y to x. So in this definition, I haven't referred to very explicitly to the category set. I kind of went right to the concept of function. But in the normal category set, I take functions from x to y. Now I'm taking functions in the other direction. Yeah.
Is it right that not all categories have opposites?
No, every category has an opposite. I just do this. And so for this exercise, you should check just with the hypothesis that C is a category, that C off is a category. But just assuming that C is a category, C off is always a category. Yes.
For the set example, if there's that, because we start with the math, there's like one set, one check, and where's the type? Are we saying that math is now empty, or are we changing this to
So, yeah, so what's happening is that we have like some concrete pre-existing stuff with their functions between sets. And now I have these things out in the world, sets, functions, type theories, and I can choose how to gather them up and package them up into a category, if that makes sense. So if I define a category set, I do it in one way. If I define a category set off, I'm doing it in a different way. So I just like switch the direction for some reason. Does that make sense? Okay. Okay, so let's start using it. Maybe it'll also be helpful to start using opposite categories. So here I defined, let me use this word. So there I defined the concept of terminal object. And now I want to define the dual concept. Dual meaning that I kind of use the notion of opposite category of initial object. So, okay, you might have seen these memes. I think we told me yesterday about category theory, where people like to abbreviate concepts in category theory. Like we saw the meme saying that a monad is a monoid in the endofunctor category of cats. So I'm going to do something similar using the notion of opposite, and then I'm going to explain it in an elementary way. So, an initial object in the category C is defined to be a terminal object or the terminal object in CI. Okay. So already defined the notion of terminal. Now I got a dual notion. or I just think about what it means if I do it in opposite category. So let me give a more elementary definition, and the exercise will be for you to check that these two things are the same. It's not as difficult as the statement about monads. Okay, so an initial object, let's say call an object, let's call it I for initial, in C, initial. If for all other objects, Z in C, which could also be I itself, we have that there is exactly one map from I to Z. Okay? And maybe now I'll call this anti-geometry, which should be a little I if you want. Okay? But now just observe that this definition, it doesn't make, the second one, but doesn't make reference to CR, is, I think, if we don't know the definition of opposite category, the opposite of this definition. Okay? So we ask not that there's a unique morphism from any object into our object T, but we ask that there's a unique morphism to any object out of our guy I. We just switched the position of Z and the object we're defining. Okay, so it's really the opposite. And yeah, it's up to you to check that if you really apply the definition to C up, that it's exactly the same. But hopefully in a naive sense you see that it's the opposite. Okay. So now we can write something like lemma, initial objects are unique up to unique isomorphism, just like before, so that's about initial objects. And this little one word, no, go here.
You might be wrong, like, behind
Yeah, I think we were here. Okay. Yeah, so we had the proof of the statement for terminal objects, which, well, it was somewhat simple for our category theoretic proof, but also complicated for someone taking category theory for the first time. But now we don't have to prove this, or we don't have to go through the same kind of argument. We can just say that this follows dually. From, let's just call it the previous lemma. So we already proved it for terminal objects. Here we're talking about initial objects. But initial objects are exactly terminal objects in whatever category we're thinking about op. Right? That's how I defined it first. We're talking about initial objects. They're really terminal objects in C op. And here's an exercise. Maybe actually, I'll strengthen this exercise a little bit. Here's an exercise that's hopefully also believable without going through the motions of proving it. That if something's isomorphic in C, it's isomorphic in C op. And in fact, the isomorphisms are given by the same data, so if there's a unique isomorphism in C, there's a unique isomorphism in C op. So we use the fact that we know this for terminal objects. Our initial objects are terminal in C op, which means that they're unique up to unique isomorphism in C op. But the isomorphisms in C op and C like basically coincide. So it's also unique up to unique isomorphism in C. So we don't have to prove it again. Yes?
To make sure I have the right intuition for initial terminal, if there are objects that are both initial and terminal, does that mean your category is all isomorphic itself? It's like there's just one guy?
No, so that's a very interesting situation. So when that happens, it's called a zero object. That happens a lot in algebra, like you're talking about the category of vector spaces that have a zero object. Maybe more relevant for you is that the like category of Haskell, which I don't know why maybe that really exists, but like if you had some kind of categorical approximation to all the programs that you can write in Haskell, that also has a zero object. Because you have one way to think about it is that you have a special undefined term in every object. And that basically means that that the initial, well, we're going to see what the initial object is in some examples in a second, so the initial object and the terminal object are the same. Yes?
So earlier you drew like a blob that had a bunch of points and they were all pointing to the same terminal object.
Yeah.
Does that mean all the sources of those points, the definition for initial objects are initial objects?
So for initial objects, we can have the dual picture, let's say. So if we have an initial object here, then we can think that like we have the rest of our category over here for some reason. And just move things around a little bit. Then we have exactly one morphism to each object. Does that answer the question?
Yeah.
Okay, so let's think about some examples. Yes, there was a question?
Is there a category, or are there categories without initial and terminal objects?
Definitely, yes. Yeah, so we had an example. I've also erased it, the category with just two different objects. No arrows here. Yes, okay, so let's think about some examples. So first example should always be set. So what's the initial object in set? Yes.
Sorry if this is too in the weeds, but I'm looking at the definition of opposite, and I've noticed that there's no definition for composition in the opposite, right? So certainly I agree that, if we have F and G in C, then we have, the dual F and G in C opposite. But how do we know that F composed of G is G opposite composed with F opposite or something?
We just define it
We just,
that way.
so we would also include in the definition the composition, and it's just that it's so obvious that we didn't feel the need to write it down.
I didn't draw it, I just erased it.
Oh, okay, I see.
And then I have this exercise to write it down more rigorously than my drawing.
Okay.
So yeah, definitely when you define a category, you as a definer have to define what the objects are, what the morphisms are, what the identity is, and what composition is.
Great, okay.
So we define that ourselves, and then we have to check that the laws follow mentality and associativity.
Okay, I was working on the proof that you gave as an exercise. I was like, wait, confused. Thank you.
Yeah, no problem. Okay, so what is the initial object in set?
Empty set?
Yes, everything. Exactly. It is like this. And why is that? So we have to check that for any set, there's a unique function like this, right? And we can always define something like this because we have to specify where all of the elements of the set go. There are no elements, so specify it clearly. Maybe it makes a little bit more sense when I just said the category of types. So what's the initial object in?
Void.
And how did Anya denote that?
Void.
Okay.
Void.
Bottom. So bottom. So sometimes it's also denoted like this, like in rock. Maybe it's denoted like this. If I remember correctly. So yeah. So we have the empty type, the type with no, like the inductive type with no constructors, which I also have defined. So since this type has no constructors to define a function out of it, you don't have to supply any information in the system. So you always get a map to NC. Okay, so you always get a map like this by the deductive principle of this guy, by pattern matching, or there's nothing to match on. We always get a map like this, and you can show that it's unique. So define, there's nothing going on, so it's not possible to have two different ones. Okay, and what about in the category of propositions? Did we talk about the terminal object in the category of propositions?
Yep.
That was isomorphism. Okay, I forgot to give the example of terminal object in prop. So what's a terminal object in prop? First.
Up, true.
True, yes, it's true. I mean, this is also maybe a bit suggestive. So, yeah, maybe I won't write it down because I put the terminal part. So the terminal object in prop is true, right? Because in prop, so to have a terminal object, we need exactly one morphism from anything to our terminal object. And we talked about already in prop, all the Hom sets have at most one morphism. So in prop, we really just need to say, or we really just need to ask that there is an implication from any proposition into our guide as terminal. And certainly true has this property, right? You can prove true from any hypothesis. So true is the terminal guide in prop. And the initial guide is then false. Yeah, also kind of implied here. So if we know false, of course we can prove anything, right? So we have that false implies everything. So there is at least one map to everything, but in prop there's at most one map, so we don't have to check anything else. So definitely false is the initial object in prop. Okay. Right, so let's see. So what about some of the other examples? Here. So what if I have a category with just one object? What's the initial object?
A.
A. And what is the opposite category of this category?
The same?
Itself, yeah, because there's no arrows to switch. So this category, it has terminal object A, and then by duality, kind of like with this proof, we know also that A is terminal, is the initial object, right? Because when we do the op, nothing happens in the same category. Okay. If we have, well, maybe first I'll do a sanity check and say if we have a category like this, with just two disconnected objects, A and B, does it have a terminal object? No, because, well, sorry, does it have an initial object? I said that. Also no, right? Because just like my argument about terminal objects, when we have an initial object, the category is connected. In the sense that ignoring the direction, there's some path from any object to any other object. And that's not the case here. So it's not initial. There's no initial object. Okay, and if I have an error like this, what's the initial object? Yes, it's A. For the same reason, for the dual reason, as the argument that B is a terminal object in this category. Okay, and then if this is an isomorphism, what's the initial object?
A and B.
A and B. Yeah, and it's for the dual reason that A and B are also both the terminal object. Okay, because we take the op of this category, we get the same category. So the terminal objects and the initial objects coincide. Yes.
Is a category equal to its opposite only if there are no errors?
Well, so this one's equal to its opposite.